Okay, let's get started. So it's a great pleasure to have Dr. Kaixuan Ni here visiting us in New Mexico from Zoom. As you can see, he's deep underground in the Gran Sasso mine with the XENON detector behind him. I visited there a year ago, and it is really that big and very impressive. So as I mentioned in my introduction in the email, the XENON experiment has recently made measurements with potential hints of new physics. Dr. Ni is going to tell you all about this today, so I won't go into it. I've known Kaixuan for, I don't know how long it's been since we met in Amsterdam in one of the dark matter conferences, and I've always been a real fan of his. He's an amazing experimentalist, and he will tell you about, this large experiment that he's been working on essentially in this area of liquid xenon dark matter experiments for pretty much his whole career. He's branching out more into the neutrino side now with the upcoming experiments like Darwin, which will be a European, I think, international collaboration that's going to make even much, much larger xenon detectors at the level of 50 ton. Is that right, Kaixuan? Yeah. So anyway, for today's talk, it'll be on the XENON1T. Just a very quick overview of Kaixuan's career. He did his PhD with Elena April in Columbia University, receiving it in 2006. She's the spokesperson of the XENON experiment. And then after that, he postdoced for a few years at Yale with Dan McKinsey, who's one of the spokespeople, I think, of the LZ experiment. Also has been working on xenon pretty much his whole career. And after a few years of postdocing, he became a professor, assistant professor at Shanghai, where he was 5 years before UCSD stole him away. And he's been there, I think, for the last 5 or 6 years. He's won a couple of awards. The most recent one is the DARPA Young Faculty Award to develop a small TPC, liquid xenon TPC, to make measurements and detections of reactor neutrinos. The novelty with this particular detector is that it's going to go down to potentially single electron detection, tens of electron volts. So if you're in this business, you know how hard that is. So with that, please go ahead and start.
Okay, thank you, Dinesh, for the introduction. I wish I would be could be at Gran Sasso Underground Lab in my background, and actually I'm in the sunny San Diego. And before this pandemic happened, I was fortunate to be in Gran Sasso at the end of last year. At the time, we were still constructing the XENONnT experiment. And the reason that we use the underground lab for this type of experiment is really to reduce the cosmic ray induced backgrounds. The underground lab has been used for many experiments in the last several decades, and even Nobel Prize were awarded for such experiments, mostly for neutrino detection. And there's the underground experiment in the Davis Cave now in South Dakota. Now it's called the Sanford Underground Research Facility. It was recently designated as a historical site from APS. And that was the first experiment that resolved the solar neutrino mystery. And for example, also the Japan, they have the Kamioka Underground Lab that first detected supernova neutrinos in 1987. Later, the other experiment like Snow experiment, and also Kamioka, they discovered the neutrino oscillations. And that also indicates that the neutrinos must have a mass, but we still don't know what's the mass of neutrinos. So there are several challenges or several important problems in elementary particle physics that we can address using these deep underground experiments. one thing that one can look for is search for so-called neutrinoless double beta decay. If that process is discovered, that would be show us that the neutrinos actually is a Majorana particle, and we can measure the absolute mass of neutrinos. That's a big deal in neutrino physics or in elementary particle physics. Now today I'm going to talk about how do we use the underground lab experiment to search for dark matter particles, or even search for solar axions. And the experiment I work on is in Gran Sasso underground lab in Italy. That's actually is not underground. It's actually a tunnel beneath 1,400 meters of mountain, high mountain. And you can even drive your car inside to the lab space, which is pretty convenient to access the lab. A little bit introduction about dark matter. Many of you have probably heard about dark matter and dark energy that occupies most of the mass content of the universe. So far, we only know 5% of the universe called ordinary matter that live with us. That dark matter, the evidence coming from large-scale structures, or even in the galaxy clusters, or even in our galaxy scale. So that means we are all living inside this dark matter halo. And that means that when the solar system is in the dark matter halo, we would expect that some of the dark matter particles, if they are particles, they should be able to interact with us besides gravity. Right? So that's something we are looking for in the past several decades. And the most intriguing candidates for dark matter, one is called WIMP, weakly interacting massive particle. The other is called Axions. So if you started at the research about 10 years ago, the Axion and the WIMPs are the most promising candidates, and there are two different type of experiments looking for them. The WIMPs are being searched for by these underground experiments, like XENON and many others, like CDMS. Axions are mostly looked for using other type of devices. You basically try to convert the axion dark matter into photons in the magnetic field and try to detect them. And there is it looks like these tiny mass axions is not, the detecting these tiny mass axions completely different from this detecting heavy mass WIMP particles. But now after 10 years, people have been developing particle detectors, and also the theory is developed that maybe the dark matter is not only so simply just a WIMP or axion. It might be other particles in the hidden sectors, or sometimes called a symmetric dark matter, that it can extend the WIMP mass down to keV. And the axion maybe it can also contains the mass below keV can also be other dark matter particles. Generically they call ultralight dark matter. So there are a whole range of mass of dark matter one can look for. And of course, if you have a detector, if you can build different type detector with different thresholds and look for different type of dark matter particles. So I will start with the WIMPs, which if we put in this plot, the WIMP is one of the dark matter candidate that is also predicting some of the theories beyond a standard model, like supersymmetry, predicts the neutrinos. And it has some cross sections with the ordinary mass particles. And if you take this particle mass and particle cross section, the cross section, and estimate this interaction rate, the WIMP will typically, with such a heavy mass and the kinetic energy, it will make elastic scattering on the nucleus and produce a nuclear recoil. The energy of the nuclear recoils typically in the tens of keV, so it's pretty low energy nuclear recoils. And because the cross section is so low, you would expect that you would have detected less than about 10 events per ton if you have 1 ton of target mass per year. So it's really low rate experiment. And that's why we have to hide beneath the mountain to shield the cosmic ray background. And even inside underground lab, we have to build a lot of shielding devices, select the purest materials to construct a detector to avoid the radioactivity. The XENON experiment started more than 15 years ago. The goal is to build a larger target mass detector, at least 1 ton. At the time, when I was grad student, my PhD advisor proposed a 1 ton detector, and it seems like a dream. And the key is actually you also need to build the detector has a very low background and very low threshold. So in this, my PhD year, I developed this with some colleagues, this 10 kilogram detectors, right? Just to demonstrate that actually the principle works. That probed the dark matter nucleon cross-section down to 10 to the minus 43 centimeters square. And then over the years, we continue to build a large mass detectors, XENON100, then XENON1T in the last few years, eventually realized this detector with 1 ton, at least 1 ton of target mass. Total Xenon, the XENON1T uses 3.2 ton. And the size about 1 meter, 1 meter in diameter, 1 in height. And recently, we just finished the construction of the XENONnT detector, which would eventually use total more than 8 tons of liquid xenon to fill inside the detector to start to search for dark matter very soon. And gradually, we push this WIMP nucleon cross-section down to 10 to the, below 10 to the 10 to the minus 47 centimeters square and continue moving forward. Darwin is a future detector that eventually will use 50 tons of liquid xenon. And that's we call the next generation experiment. The experiment started in 2002, founded in the US. And although the experiment location is in Italy, it's a very beautiful underground lab inside the national park. And many of our students and postdocs, enjoyed living there, eating a nice food, and also working in the best experiment. And the good thing, we have expanded it, from US to Europe, and even recently Japan and China joined a collaboration. And many of our former students, including myself, eventually become faculty and leading a university group to join the entire collaboration. And even within this pandemic, we cannot come together. We have constantly, weekly, several meetings every week, and it's working pretty well. So let me now go into some details of how the detector actually works. So we call this is two-phase time projection chamber. Some of you may have learned about time projection chamber, which we call it time projection because when the event interacts, we would have 2 signals, one as the trigger, the other would take some time to drift and produce another signal. And using the drift time, we can tell the position of the event in the detector. The main target is a liquid xenon. And then we have a S1 as scintillation trigger from the WIMP dark matter interaction produce a nuclear recoil. Nuclear recoil will produce a scintillation light, and the ionization signals will drift into the gas phase. That's a critical step, where in the gas phase, there's a strong electric field that amplifies this ionization electrons into electroluminescent signal, we call S2. And this S2 is also detected by the photomultiplied tube arrays located in the top and the bottom of the TPC. By using this S1 And as to signals from each event, you would be able to reconstruct the energy and the three-dimensional position of each event. And we rely on this information to reduce further the background, either coming from the outside or coming from radioactivities. And I will not go into the details why the liquid xenon becomes so popular in the search for dark matter. It has several important aspects, but most important is that we can really build it in a reasonable cost and reasonable cryogenics, and we can reduce the background and use the signals that to search for different type of particles. This is a design showing how the XENON1T detector looks like. The central detector is the field cage and viewed by the top and the bottom PMT arrays. So these PMTs, the bottom PMT actually is immersed in liquid xenon at cold temperature of 165 Kelvin. And they are also sensitive to the ultraviolet scintillation light of liquid xenon. So it's specially designed. In addition, these PMTs has very low radioactivities. So the material is specially selected to build these photomultiplier tubes. And actually there are not many choices in the world that can provide such kind of PMTs. This one is from Hamamatsu. So once we construct PMTs, we put in looks like hanging on a cryostat, where eventually the liquid xenon will fill inside and cover the entire TPC up to the gas region. And the detector doesn't look like very big, right, compared to the human size, but we have to put this detector enclosed inside the vacuum cryostat and place the inside a 10-meter diameter water tank. You may wonder why you still need the water to immerse this liquid xenon detector. So water provides additional shielding for any background coming from the outside, like from the rocks, from the instruments outside the TPC. And in addition, we have instrumented the water tank with the photomultiplier tubes. So if there is a muon or cosmic ray muon event coming into the underground lab, we can still veto the event. So even at 1,400 meters of deep under the mountain, there's still about 1 muon event every hour, striking about 1 meter square of area. So that muon veto gives additional background suppression. That's the XENON1T, the detect how it looks like. Then we have this three-story building that provide the servicing instruments to the detector. On the bottom floor, there is a spherical, we call xenon storage tank. Can store up to 7 tons of xenon. And then there is electronic in the middle, but on the top part is our most important instrument to provide a cooling to the liquid xenon and also a purification system to constantly purify the xenon in order to have it clean enough to get the signals out. The experiment started data taking in November 2016, and then continuously accumulate data. When we say we take data, it's not like cloud experiment. You have to have the accelerator to produce events, then you take data. For us, we just wait. So the particles coming from the universe, coming from the galaxy, right? So dark matter just going through our underground lab, and we are waiting for this particle to interact with our detectors. We just increase continuously collecting the data. The rate is pretty low, like we have events rate of few hertz inside. There's 2 tons of active target. So this is low background experiment. And we take data until February 2018. These are the data we published so far. We took additional data called a Science Run 2 until the end of 2018. But these kind of R&D runs, and also at the same time to check some of the calibration sources. And then we ended at that point to prepare for the XENONNT installation. If you are interested, you can always see, how the instrument works and how we analyze the data. We already published some results in the WIMP search, many WIMP search results. And in the middle, we accidentally, discovered we actually was the first time we detect the XENON 124-element double electron capture. So this one has a very long half-life, and it was predicted by theory. It's a standard model process, but it was never discovered before. And that shows, how this kind of low background experiment may sometimes give you surprises. And we later also searched for very light dark matter using so-called Migdal effect, and even use S-only. Denise just mentioned that I want to build a detector that's sensitive to single electron down to a few tens of eV of threshold. So this is already being tried in the XENON 1-ton experiment to search for very light dark matter. Now today I'm going to talk about our recent results, so-called the low energy. We observed some excess events at the very low energy region, but it's in the electron recoil channel, not the nuclear recoil channel as for WIMPs. So, and this is really some new result that made us, puzzle for the last 1 or 2 years. And eventually we checked all the things and published the paper in this June. Before going into details, this is a typical type of waveform or event that you would expect from a WIMP nuclear recoil. The S1 is very low, a few photoelectron detected by PMT. S2 usually is larger because it's amplified in the electroluminescence region, the gas region, and also it's wider. And use this event distribution, the light distribution in the PMT arrays, we can get information on S1, S2, and the positions. And as I mentioned, the larger detector, you can shield this external radiations. This is so-called a fiducial volume cut. Because external radiation like gamma rays or neutrons, they would interact near the edge of the detector. But for WIMPs or neutrinos, they are so weakly interacting that they would interact uniformly inside the detector. By choosing the inner volume of the TPC, we could be able to reduce the background and do a more sensitive search for dark matter or new signals from the neutrinos. So this is so-called a fiducial volume cut. Now, in addition to this fiducial volume cut, I just mentioned there are 2 types of signals. One is nuclear recoil, one is electron recoil. And they have different DEDX in the detector. The result is they would have a different ratio between the first scintillation signal and the second S2 signals from the ionization. And this plot is from calibration data. We use radioactive sources to calibrate how the electron recoil, mostly background, respond in our detector. And the nuclear recoils, we use neutrons to calibrate. And usually the nuclear recoil will have a lower S2 over S1 ratio compared to the electron recoil. By doing that, we can, if you want to search for WIMP nuclear recoil interaction, you would search for in the red region, right? If you have some new physics model that would produce electron recoil, you would search in the black region. So that's how we look for the signals. And the energy is constructed based on the size of the S1 and S2. For nuclear recoil search, I just mentioned. So this is the the event, all the events, each dot is one event detected in the XENON1T detector from our science run 1, and each dot is event. And you see that most of the events are located in the top part, the black region, the electron recoils. These are the main background electron recoil. And the nuclear recoil would reside in this purple, 2 sigma band. This is a region that where we expect 200 GeV WIMP would produce. And there's lower part, there's also some events that is coming from the surface. If you look at them in the R space, and they are mostly near the edge. So they are coming from some instrumental related surface events that can be easily rejected. Now in this WIMP search data, we are looking for events in this purple region, and I found few events. And let me just explain, that the size of the event indicates the likelihood, the probability of this event is from a 200 GeV WIMP. But there are also probability of this event coming from, for example, the surface, this event, right? Also this event, for example, coming from neutrons. And this is based on our likelihood of the neutron background. So from this search, we didn't conclude any events, coming from the WIMPs, and we can only construct a limit of the WIMP interaction. And these are the results we already published a few, 1 or 2 years ago. And so far it sets the most stringent limit for WIMP nucleon spin independent interaction and the WIMP nucleon spin dependent interaction. And even we made the first limit on the WIMP-Ion couplings. So if you're interested, you can look into these papers. And these are for WIMP masses above 6 GeV. So far is the most stringent limit. Now today I want to focus more on this electronic recoil, the search for new physics in electronic recoil or electron recoil signals, which is in the green band as shown here, or the black events indicates this electron recoil, right? You want to search whether there are some new physics over there. In fact, if you look into the literature, there are many ways that even dark matter can scatter on electrons, produce an electron recoil, if the dark matter is light enough. And there are also other physics we can look for, like solar neutrinos can scatter with electrons, produce electron recoils. And Axion, solar axion can also interact with electrons to produce electron recoil. And then there are all sorts of bosonic dark matter models, such as Axion-like particles or dark photons that can be absorbed and produce electron recoil signals in our detector. I will briefly explain this, the 3 signals as we are looking for and as we publish in this paper. The first thing is the solar axion. I mentioned earlier the QCD axion, which is a very light particle compared to WIMPs, and they can also be dark matter. But QCD axions, they are too light, and if they are the dark matter particle, they are also not moving very fast. So the kinetic energy of this QCD axion around us is very, very small. The XENON1T would never be able to detect this dark matter axions. And we have to rely on other method. But the axion can also be produced in the sun. And typically there are 3 couplings that used to produce the axion, so-called solar axion. These 3 processes are governed by these 3 couplings. GAE is axion electron coupling, GA gamma is axion photon coupling, and GAN is axion nucleon couplings. They would produce axion flux that arriving at Earth from the sun, shown on the bottom left figure, and have a signature about from down to 1 keV. If you below 1 keV up to the 14.4 keV of the iron 57 line from the GAN coupling. Now these three couplings produce three different spectra. And once it arrives in our detectors, they have to couple with the electrons in the detectors. And this right figure is the what we expect how the solar axion will be detected in the XENON1T detector. The rate, of course, that would determined by these couplings, right? So for example, the primal coupling mostly the axion will convert to photon or axion-photon coupling, produce axion, come to the detector, and then it will be detected by this GAE coupling. That's why this primal spectrum would be proportional GA gamma squared times GAE squared. And this GAE squared determines the probability of this solar axion being detected by the XENON1T via this axion electric effect, which is similar to the photo electric effect, except it is proportional to the GAE squared. Now, if you look at the spectrum, if GAE is 0, then the XENON1T would never be able to detect solar axion, right? But if we detect some signals, that indicates GAE must not be 0. And the GA gamma or GAN is more, will be less well constrained by the XENON1T experiment. This is how we detect solar, how we search for solar axion in the XENON1T detector. Solar neutrino is, we have solar neutrino has been detected by many experiments already, and even the lowest energy PP reaction neutrinos has been detected by Bosonic, also at the Gran Sasso on the Gran lab. And these detections all using the solar neutrino electron scattering. And XENON1T, of course, can also detect the solar neutrino electron scattering in a target. But the rate is shown in the blue part on the right figure is very low, and it's even below 2 orders of magnitude lower than our background. So at this moment, we still cannot detect solar neutrino electron scattering. But maybe in the future, the Darwin detector will be able to detect the solar neutrino electron scattering. But if the neutrino has a magnetic moment or large magnetic moment, and it will enhance the event rate being detected by the XENON1T or similar type of experiment. So if we assume the neutrino has a magnetic moment of about 3 times 10 to the -11 Bohr magnets, that would enhance the event rate typically below 5 keV. So this 3 times 10 to the -11 is the current limit from Bosonic experiment for a larger neutrino magnetic moment. Now, the reason that we are interested in neutrino magnetic moment is that if we detect such a large neutrino magnetic moment, it means that there's some new physics, and it indicates that neutrinos has a Majorana nature. So that's the second new physics we're looking for. The third one could be called bosonic dark matter, such as axion-like particles or dark photon. These typically would produce a monoenergetic electronic recoil peaks. So that can be easily searched for. You just search for a peak over your background. And the rate is typically governed, for example, for the axion-like particle, it would be governed by this GAE square. So this GAE is similar to the solar axion GAE, but in this case, we call the axion-like particle as a dark matter candidate, but it's not a QCD axion that would solve the strong CP problem. But it can be a candidate for dark matter. And also for the vector bosonic dark matter, like dark photon, and this is determined by the rate is determined by the kinetic mixing of dark photon coupled with the standard model photon, this kappa. So we can constrain this kappa parameter based on the rate we detect in our experiment. So to summarize, what we are looking for is to look for some excess of events that over the all known background in electronic recoil channel. Now, so what's our known background? One major background is the internal electronic recoil source. This source, one is krypton 85 beta decay, another is the radon. So krypton 85, the krypton, is also a noble gas. It can mix with the xenon, right? If you buy the xenon, the purest xenon gas from a commercial company, and they will give you, say, oh, we have a 99.9999% of xenon, and it still contains some elements like krypton at about 10 parts per billion level. Now, the krypton 85 was produced in the nuclear test over the last century, and it contains in this krypton at the 10 to the negative 11 level. So we still have a trace amount of krypton 85, and which beta decays and produce low energy electronic recoil signals in our detector. So if you buy the xenon and you fill it into our detector, and you start see event rate as shown here. So in the September 2016, when we started experiment for the detector, we started to collect data, we found a quite high rate. This high rate is still, in terms of detectors, experiment high rate, but it's still quite low. And this is coming from krypton 85. We can even use a residue gas mass spectrometer to measure what's the krypton concentration in our xenon that is consistent with the event rate we detect in our TPC. And we have this special device. It's called a distillation column that using the different boiling points of krypton and xenon to remove the krypton from the xenon. And after we run this distillation column, we saw the rate drops continuously, and until about November, December 2016, the rate is dropped below, the lowest rate ever achieved previously by PanX2. And at the end of December 2016, the rate didn't go down further. And we checked the measurement from this RGMS of the krypton rate. We found that krypton actually is already much lower than our background rate. So what's the background coming from? This was understood as coming from radon. Radon, you're probably all familiar with that in your basement. If you don't have a good ventilation, you would have a lot of radon from your basement. It eventually becomes unhealthy. And it has a half-life 3.8 days and coming from the breakdown of the uranium decay chain. So the radon is one of the daughter element of uranium decay chain. It decays. And by alpha decay or beta decay, the alphas typically have a high energy and we don't worry about them. But in the decay chain, there's this lead-214 beta decay, lead-214, and this would produce constantly a beta decay that contributing to the background in our electronic recoil channel at low energy. Now, we know that the radon natural level in the air is about 0.4 picocurie per liter. If I compare it to another unit of becquerel per cubic meter. So you have about 15 decays of radon in the air per cubic meter of air, about 1 kilogram of air. In the XENON1T target, our measured rate is about 5 to 10 microbecquerel per kilogram. So it's about 6 orders of magnitude lower than the radon in the air. Now still, this is our major electronic recoil background in the XENON1T detector. We actually measured this radon contribution from all the components that directly touching the xenon target, and we sum them together. They are consistent with this measured background. So radon, we understood them. They are coming from the emanation of different parts in our detector system. And they are the major background when we search for the electronic recoil signals. With all this consideration, in fact, although radon is the major part, we call it internal background, there are other 8 elements that would contribute to the electronic recoil. So it's not so trivial. We have to consider all the known background, such as the XENON124, which we first actually observed this double electron capture peak in 2019, and then it immediately becomes our background. And there's also XENON136 is a double beta decay. We have about 9% of XENON136 in the liquid xenon as an element. And it has a double beta decay, and it contributes some background in the low energy, not major, but some background. And we also have activated background coming from a neutron calibration. And right after neutron calibration, some of the xenon element is activated, and they would decay with typical 10 days or 5 days of half-life, but still contributing in some part of our search. The external background is mostly coming from gamma rays, from the construction material, or solar neutrinos. These are subdominant. So we understand all this 10 component background, and then we even separate the search into 2 different regions. One is right after the neutron calibration. So on the top figure on the right, showing this 10 components sum up into our background model for the right after the neutron calibration. And the lower is more cleaner, farther away from the neutron calibration. So you see the differences of the 2 background models. The most of the difference is from above 30 keV. So below 30 keV, the major component coming from radon, and then the second krypton 85, all similar. So in the low energy region below 30 keV, the backgrounds are similar. This is our background model. Now we have to compare with the data we collected, right? So we made a comparison of our data with this 10 component background. The black dots are all the measured event rate in energy from 0 to 200 keV that we used for this search. And they matched pretty well in most of the regions. Now, if you look more carefully, you find that one region that is not so matched well. This is really at the lowest energy region here. So we discovered this, actually the graduate student discovered this, one graduate at UCSD, another at Chicago, together with a scientist at Zurich. And they found this about more than 1 year ago. And they discussed this at the analysis meetings and also what are those events coming from. If you blow up this into the low energy region, it's more clear. So this mainly these events, most of the red is B0, we call this a background model. This sum up all the 10 components. And the data just show clearly in excess below 7 keV and keep rising up at low energy, towards low energy. If it's just by counting, total events in this region is 285 events. And expected from this B0 background model is 232 plus minus 15. So this is already indicating at least a 3.5 sigma fluctuation over the background. And of course, at the beginning, we were not so excited about it. Maybe, it can be, some analysis can be, mistake or maybe cuts. So we took a lot of time to check what's going on with that. And eventually, we checked this energy reconstruction. We check the instrument background from other background, and we check even the beta decay spectrum. Maybe the beta decay spectrum has a uncertainty or problem there from theoretical aspects. And none of them is a problem. So for energy reconstruction, we have two calibration sources to verify. One is a radon 220. Now, radon 222 is our main background. Radon 220 is our injected radon source, which has a similar spectrum as radon 222 background. And it shows no excess at low energy. We even had a argon 37 calibration source, which has a 2.8 keV peak. This is injected at the end of the run, so right long after the science surge. And it shows a clear 2.8 keV reconstruct pretty well. And for example, the lead 214, we even team up with external expert, to see what's the beta decay spectrum really down to below 10 keV. Because we use Jiang4 to simulate, and it shows some rising at low energy, but this IAEA live chart shows a downward. So we were really not sure. And the work here, we use this latest calculation from this theorist that shows a slightly up. But this only accounts for 6% of uncertainty on the shape. To account for this total excess, we have to have 50% in order to account for excess. So this also cannot be the reason for the observed excess. Now, we didn't jump to the new physics immediately, and then we consider maybe there's some other background that contributing to the electron recoil we didn't consider. One is tritium. So tritium is also a beta decay, and it was detected by some dark matter experiment using germanium target before, because tritium can be created cosmogenically also in xenon. And people even have calculated what amount of tritium will be produced in xenon. The amount is very negligible, considering that once the xenon is moved underground, the tritium will decay, and once the xenon is filled into our detector, the tritium would stay in the gas xenon instead of mixed in the liquid xenon. And further, this tritium or hydrogen would be removed by our purification system down to part per billion level. And based on this argument, this tritium would drop down to a negligible level. But we still can fit this excess with the tritium spectrum. And that spectrum would produce a tritium of about 3 trillion atoms per kilogram of xenon. And that's still 2 orders of magnitude above our estimated based on the condensation and purification. So that cannot explain why we would have such a high rate if it's indeed due to tritium. The problem is our background is so low with the 3 trillion atoms per kilogram xenon, there's no other ways to measure them directly. So we keep that as an option, but it's very hard to explain. Another source of background, we all deal with this radioactive backgrounds, is argon 37. Remember, I mentioned that we use argon 37 as a calibration in the end. But argon also presents in the air, and there is a trace amount of argon. Now, if argon is leaked into our detector due to an air leak, what would be the rate, right? So we measure this argon 37 in the air around the XENON1T detector, which is less than 3.2 millibecquerel per cubic meter. And we also estimate the air leak rate, the maximum air leak rate that's possible based on our krypton xenon measure, because krypton is also in the air. So if there's air leak, you should also see the rise of krypton, but we didn't see very high rate rise. So that give a maximum leak rate of 0.9 liters of air per year into the xenon detector. Getting this two together, we would expect the maximum of 5 events per ton year. That's in our search. But we observe 65 events per ton year. So that argon 37 cannot explain the observed excess either. In addition to that, if we fit the peak into our excess, it gives a best fit peak of 2.3 keV, not 2.8 keV as from argon 37. So that was excluded due to these considerations. Now, without any other suggestions or unknown background, and maybe these are coming from solar axion or solar neutrinos. So if we interpret this as coming from a solar axion, and if you still remember my earlier talk about the three components of solar axions, they have this shapes based on the three different couplings, and they can fit this excess pretty well. And this fit gives a solar axion favored over background at 3.4 sigma. Slightly better than the fit from Tritium. Maybe it's due to this shape. And if we interpret this rate converting to the couplings, of course, the GAE equal to 0 is ruled out, right? If the GAE is 0, we would not be able to test solar axion. And then the parameters would be inscribed in the cuboid with these parameters, three different couplings. I just show one plot showing the parameters of GA gamma and the GAE. The XENON1T, this excess would be produced by the parameter in this blue region. So either very small GAE but high GA gamma, or fixed GAE, but regardless of GA gamma is very small, it's no problem. Now this region has been excluded partly by this CAST experiment. CAST is a solar axion search experiment that typically looking for the axion converting into photon. So it's very sensitive to the GA gamma coupling. So lefting over only this below this green line is still allowed by CAST. But if you look at, there's also astrophysics constraint from red giants, white dwarfs. These are using different ways, astrophysics constraints. So this is in strong tension with if the parameters that we observe is indeed about 3 × 10⁻12, that will be much more already excluded by this astrophysics indirect searches. So that's one concern. Solar axion, solar neutrinos, if a neutrino has a magnetic moment, that can also explain our data at 3.2 sigma level. And that would give a neutrino magnetic moment of about 123 × 10⁻11 Bohr magnet. And this is not in tension with the direct measurement from Boroxino is a solar neutrino experiment, and a gamma is a reactor neutrino experiment. So we are not in conflict with this direct measurement. But still, it's the same, similar to the Axion case, we are in conflict with this astrophysics constraints from global clusters and white dwarfs. So this remains some mystery why we will see that if a neutrino magnetic moment is so high. And then we fit the peak, as I presented earlier, it's the best peak is 2.3 keV, and that can be used to explain if there is axion-like particle or dark photons at 2.3 keV. The significance is about 3 sigma globally, or 4.0 sigma local significance. You can search for peak in the any range, mass range, and we provide this constraint for this GAE coupling or the kinetic mixing coupling for dark photons. And this so far placed the most stringent constraint across from 1 to 200 keV. Because in other region, we didn't see a peak. Only at this about 2.3 keV, there you see this region, we have at least a constraint. So these are the 3 new physics searches we performed in this low energy excess, if we want to explain this excess due to new physics. And after our paper released in June, there are a lot of papers coming up to explain the signal. Most of them are from from theorists. Only a few papers from experimental to check out data, mostly on tritium or argon or reconstruction. Even PENA-X is one of the experiments has the second lowest electron recoil background in our field, and they didn't find any conflict. And for this solar axion, solar neutrino, bosonic dark matter, and there's even boosted dark matter that has a very high speed, or inelastic dark matter, and even some explanation connected to stereo neutrino or black holes, or even hydrogen decays. So a lot of interesting and exciting. I would say, our paper just triggered some exciting summer for some of the people in the field. But we still cannot confirm which one is coming from. And for experimentalists, we want to have the next check. That is the XENONNT experiment that we just finished the construction before the pandemic hit Italy. So this is the time projection chamber assembled in March 2020. It has a much larger target mass, about 3 times larger than XENON1T. And we further reduced the nuclear recoil background. That's for the WIMP search. We have a gadolinium doped water would have a neutron veto. We also reduced the electronic recoil background by reducing the radon, as I mentioned. That will be particularly interesting for the electron recoil search. And we also improve the signals. Starting the beginning of this month, we start field the detector with the liquid xenon. And right now, it's about half filled, about photon. And commissioning, which means we'll detecting signals in the next few months, try to clean up the xenon using purification, reduce the krypton and the radon in the liquid xenon. Then in early next year, we hopefully will start a science search. Just give you a few pictures of the experimental apparatus from XENONNT, electrodes and larger PMT arrays, and eventually this assembly of the TPC. That was an exciting time, and after that, all the students, people just went back to their home institutions. But we still had a few people on site, our Italian colleagues, and they continue clean up the around, and also keep the vacuum inside the cryostat, and finish the liquid purification installation and neutron veto installation. And we will also commission a radon-free pump, and we have a special radon distillation system will be commissioned after we started the XENON run. So my last slide, just give you some perspective in the next year. Because XENONT not only it has 3 times larger target, but it will have expect to have a 1 order of magnitude lower radon background. It will have much better sensitivity. We expect in a few months of data taking, we should be able to discriminate a solar axion with the new neutrino magnetic moment or tritium hypothesis. For the WIMP dark matter search, it will be will improve the sensitivity from XENON1T. So right now, the most stringent limit down to 10 to the negative 48 centimeter cross section. And that would take 20 ton year of search, which means at least 5 years to reach down here. I would say starting from next year, we will have a new exciting search for new physics that not only including WIMPs, but also axions, also maybe connect to the neutrino sectors. Thank you.
Thank you very much, Kaixuan. Clapping from me. So I'm opening up for questions. You don't have to raise your hands, just unmute and please go ahead and ask questions.
I have a question regarding the photomultiplier tubes. I'm just wondering, is there any particular reason for using them as opposed to any kind of other detection method?
So we detect the scintillation light, right, S1, and then later amplify the S2 signal. amplified electron recoil signal, electron ionization signals to S2 and detect by this photomultiplier tube as well. So that can give us really low threshold. We typically, for the S1, we require 3 photoelectron of threshold, which about 1 keV threshold. And if you rely on S2, you can go down to sub keV threshold. So that's the goodness of using PMT to detect light. If you want to detect charge using charge sensitive amplifier, then you would typically have 100 keV of threshold, right? And that's one thing why we want to use the photomultiplier tubes. And as I already mentioned, this tube is typically designed with low radioactivity, and is also sensitive to the vacuum UV light of xenon, and it's very fast. Some new development, such as using silicon photomultipliers, these are still being developed maybe for the next generation experiment. We're also considering them for the Darwin detector.
Okay, thank you very much. I was mostly curious about silicon photomultipliers, so thank you for letting me know about that.
Let's see, I have an elementary question. What if dark matter is due to several stable or nearly stable particles? What sort of signal would you expect, and what limits do you put upon that from your observations so far?
You mean if dark matters contain several components, for example, maybe some of them are WIMPs, some of them are axions?
Well, not just WIMPs or axions, but it could be fermions and bosons that we haven't even thought of.
I think there are many models, and so far many of our limits, if you see all these limits, we assume dark matter is just one component. But there are also some models, with different components or composite dark matter, and that can be, depends on whether they would have a coupling with standard model particle. They can all be searched in our experiment. For example, some of the ineless dark matter seems to be, triggered, by our excess can also be searched. So it depends on the model, but there are many possible ways, as you see from the list of the paper put out by the theorist.
Right, thank you.
Other questions? Can you go back to your slide showing the electron excess as a function of energy? Any one of them? Yeah. So have you guys interpreted this from the point of view of regular WIMP dark matter using the Migdal effect?
No. For the Migdal effect, we have a paper on this using this electronic recoil, but we didn't interpret. We take this, we only put a limit. And maybe an interesting suggestion.
Yeah, I mean, since you're looking for, you're proposing new physics down here using, bosonic dark matter ALPs. Why not just, you're seeing events from, tens of MeV dark matter, where you only see the electrons from Migdal.
Yeah, I should check. Maybe the Migdal effect has a different spectrum, but I should check back. Maybe we should interpret it as a Migdal. But I would let you know.
Yeah, I don't know what the spectrum should look like, but you should definitely see more lower energy electrons relative to higher energy. So it should be falling in some way.
That's right.
But I don't know what the actual spectral nature would look like. But yeah, I was puzzled why that hadn't come out. I figured you guys were working on it.
Right. I will check.
Yeah, that's great.
Thank you.
Other questions? Okay, if not, Kaixuan is happy to stay on. I'll go on speaking with him for some time, but let's thank Kaixuan again for an amazing colloquium. It was really interesting, and I'm looking forward to the new results, hopefully within a year instead of next 10 years like normal in dark matter. Thanks again.
Thank you.
So Kaixuan, I had a question regarding some of these limits that come from astrophysics. If you can go to some of those, just any one of the plots where, for ALPs or something like that, where they, yeah, like this one.
Right.
So the red giants and white dwarfs, it says that the allowed region is leftward of this. Of
Yeah,
these.
only the left are allowed. So it's
Yeah.
really
Yeah.
one planet lower than our interpretation.
Right. I always see these, in regards to axions, the HB stars. Can you say something about this? Can you explain some of this?
I asked my astrophysics colleagues, and they say this red giant and the white dwarf limits are quite robust.
What are they from? I mean, what exactly are these limits? How do they calculate them?
It's calculated from, you look at how the energy loss of the stars, right? And if the coupling is large, then they would lose energy much quicker.
The axions would take away the...
Right. It's the same for the neutrino magnetic moment. It's the same thing.
Right.
And then you would not be able to, if they lose energy too quick, and it will be completely different stars.
So it's a question of how old these stars are that we observe, and they wouldn't have gotten to that age.
Yeah, I think that's along that way.
Okay. Why are you online? I guess he's gone.
I want to show you a spectrum of the migdal.
Yeah.
Share from our paper.
Mm-hmm. Yeah, this one.
You probably see this.
Yeah.
You can look at S1, S2 data, and the migdal they're looking for from 1 keV, right? It's indeed, if you look at 1 GeV.
Yeah, this is what I was thinking of. This is the paper that got me started in all of this.
Right. So 1 GeV going up.
Yeah.
And we can just fit that into our spectrum.
Yeah.
Yeah. Maybe we can put some even instead of the limit that we shown here. The has the very strong limit.
Right.
Is some region that.
Yeah.
Is it just below 1 GeV? I would say, right? Because if you look at this, the dash line is 0.1 GeV, would be much lower than our region. So must be between 100 MeV to 1 GeV.
Right.
Mm-hmm. Or 2 GeV. Yeah.
If you show your data, if you couldn't go down a little bit and just show the data.
The data here,
you cut off the data below 3 or 3 photoelectrons.
But the data is this. This region, the electron recoil surge is also cut off at 3 PE.
Right.
So basically, this is the same data. It's just like here, we didn't consider all the electron recoil background. We just consider all of them are electron recoil background.
I see.
That put a weak limit.
Right. That's right.
Mm-hmm.
Yeah, it'd be interesting.
Thanks for suggesting. Yeah, I think I should point that to them, and then maybe it's from migdal. That would be nice.
That would be amazing. Yeah. Very nice.
It's amazing that we can actually search for so many things, and not only WIMPs.
Yeah. So the neutrino floor you expect to hit in not the end one.
Right. N-ton will not reach the neutrino floor, but it will touch the neutrino signal from the solar neutrino, boron 8 solar neutrinos, coherent scattering.
Coherent scattering, right?
Yeah. that will touch. That's about similar to 6 to 8 GeV WIMPs.
Yeah. Yeah, that's right.
For the rest, this atmospheric neutrino or diffuse supernova neutrino background